Anyone who's worked in an office in Ghana knows the feeling, right? That heavy, oppressive afternoon heat. It just crushes your ability to concentrate. And what's the first thing everyone does? Scramble for the AC remote. But here's a thought. What if the problem isn't just the sun outside? What if the actual walls of the building are the real villain?
Okay, let's paint a picture. Just imagine it. You're in Kumasi, it's a hot March afternoon, and you walk into an office building to escape the heat. You're thinking, relief. But nope, you don't get it.
Instead, what hits you is this thick, heavy air. It's almost stagnant. Sure, there's a ceiling fan up there, but all it's doing is pushing the hot air around. You know that feeling? A room that's just been baking in the sun all day long?
And get this. If you were to check the temperature, you'd see it's 36 degrees Celsius. That's almost 97 Fahrenheit, inside the building. So what's the only option? You blast the AC, which, sends electricity bills through the roof and puts a massive strain on the power grid. So you gotta ask, what is going on here? Why are these buildings basically acting like ovens? Well, a team of researchers at the Kwame Nkrumah University of Science and Technology, that's KNUST, they dug into this exact question. And what they found is, well, it's kinda surprising, but also brilliantly simple.
All right, so the investigation zeroes in on one main culprit, the Sandcrete blocks. The ones used to build pretty much every office there. Now, to really get why these blocks are such a problem, we need to dive into a little bit of building science. Okay, so it all boils down to this concept called thermal mass. And the easiest way to think about it is like a sponge, but for heat. A material with high thermal mass, it soaks up heat from the sun all day, holds onto it, and then lets it go really, really slowly overnight when the air gets cool.
So here's the showdown. On one side, you've got Sandcrete. It has super low thermal mass. So forget the sponge analogy. It's more like a piece of paper. Heat just zips right through it into the room. But then you've got concrete. It's the total opposite, high thermal mass. It's a thick, protective buffer that absorbs all that heat and keeps the inside shielded.
So, armed with this knowledge, the KNUST researchers started testing things. They came up with 3 specific design changes. Think of them as 3 levers you can pull to cool these buildings down. And the best part? All of this is without touching the AC.
Lever number 1 is the big one. It's the most straightforward fix. Just change the wall material. So what happens if you ditch those useless Sandcrete blocks and build with high-mass concrete instead? Let's see. And wow, the results are, well, they're dramatic. Just look at this. Making only one change, switching to concrete walls, dropped the peak indoor temperature by a full 3 degrees Celsius. That's huge. A massive difference from just swapping out the material. Okay, lever number 2 is so simple, it's beautiful. Think about it. Most offices are sealed up tight all night long, right? So they just trap all that heat inside. Night ventilation is the answer. You just use basic fans to pull in the cool night air and flush all that stored heat out. It's like hitting the reset button on the building's thermal sponge for the next day. And you won't believe the impact. This one simple strategy, just running fans overnight, cut the number of uncomfortably hot hours inside by 42%. I mean, that's almost half. It's a classic low-cost, super high-impact solution. So the third lever they looked at was window size. It makes sense, right? Smaller windows should let in less heat from the sun. And since Ghanaian offices often have these huge windows, the researchers tested what would happen if they reduce that area. And yeah, it definitely helped. It knocked the peak temperature down by as much as 1.8 degrees, but the researchers pointed out that this was kind of modest, mostly because the buildings they modeled already had good shading over the windows. So the real takeaway here is, yeah, shading is super important, but those first 2 levers, the walls and the nighttime ventilation, they're the real heavy hitters. Okay, so we've got 3 solid strategies on their own, but this is where it gets really cool. What happens when you stop pulling these levers one by one and start combining them? Just check out these numbers. So concrete walls by themselves, that's a 3-degree drop. Night ventilation on its own, about a 2-degree drop. But when you put them together, boom, the effect gets amplified. You get a 4.3-degree reduction. It's because the high-mass walls and the nighttime flush work together as a team. Each one makes the other even better. That, right there, is synergy. Let's just stop and appreciate that number for a second. A 4.3 degrees Celsius drop. That's about 7.7 degrees Fahrenheit cooler at the hottest part of the day. And remember, this is all with 0 air conditioning. That is literally the difference between an office where you can actually work and one that's just unbearable. Which, of course, brings us to the elephant in the room. If the science is so clear and the solution is so effective, why is almost every new office in Ghana still being built with the exact wrong material? Well, the answer, as you can imagine, is complicated. For one, concrete costs more upfront. People are just used to how Sandcrete looks, but maybe the biggest roadblock is something called the split incentive problem. Think about it. Developers are the ones who build the offices, but they're not the ones paying the crazy high electricity bills. The tenants are. So there's just no financial motivation for a developer to spend a little extra to make a building cooler and more efficient. And when you tack on the fact that building codes don't even mention thermal performance, you can see why the market is totally stuck.
There's a quote from the property economist which covered this research, and it just hits the nail on the head. He said, "The building material we default to, for reasons of cost and habit, is among the worst choices available for the climate we actually live in." Just, wow. It says it all, doesn't it?
But here's the good news. The research doesn't just point out the problem, it actually shows us the way forward. What this proves is that this isn't some impossible technical puzzle. Not at all. It's a challenge of policy, and it's a challenge for the market. And the path forward is actually a pretty clear 3-step fix. Step 1, update the building codes. You have to set minimum standards for thermal performance. Step 2, make developers disclose how much energy a building is expected to use. That gives power back to the tenants. And step 3, we've got to bake this science right into the education of our future architects and engineers. And that really leaves us with one final, kind of staggering thought. You see, this isn't breaking news. The main research from KNUST that was published all the way back in 2013. The knowledge, the science to build better, cooler, and more productive offices has been sitting right there for over a decade. So the real question is, when are the policies and the market finally going to catch up?